Hi, in this video we are going to talk about the concrete implementation of the maze problem. So first of all, we are going to represent the maze with a two-dimensional matrix or two-dimensional array, or a matrix, as we have discussed. And of course we will have a class maze.java. And here I'm going to store the maze table, a two-dimensional array, and the solution table is going to have the same size as the maze table. And I'm going to initialize it with zeros. Okay, so we are going to get the maze table from outside with injection, and I'm going to calculate the maze size, which is, because it's a quadratic matrix, which means that it has as many columns, as many rows. I will calculate the maze table.length. It is going to give us the number of columns or number of rows, whatever, because they are equal. Then I will have the solve matrix, and it is quite the same. If you may recall, for coloring problem, Hamiltonian cycle problem, Knight's tour problem, and Queen's problem, whatever, we are going to do the same. We are going to use backtracking. First of all, if there is no solution, we start at the 0, 0. That's why these are the indices, the x and the y coordinates. If it's going to return false, then this means that no feasible solution has found. Otherwise, there's a solution, so we show the results. So it is the solve method is quite the same as we have seen. So if we have finished, as I said earlier, we have to check on every iteration whether we have finished the exit or not. The finished, it means that we have at the last index of the x and the last index of y, which is the last cell. And if there's a path, then I will denote it with 1. And otherwise zeros. And of course return true. If we are not at the last cell, it means that we are not at the exit. We return 4. We are not finished at all. Okay, then we have to check whether the given cell is valid. What does it mean? We have to check that whether we are inside the maze table, which means that the x is not equal to 0, and less than, okay, if it's less than 0 and greater or equal to the maze size, it means that we are outside the scope. So we have to return false. It's not a feasible solution. We have to do the same for the y position. And it means that if the maze table with the x and y coordinates is not equal to 1, it means that that's a wall. We denote the wall with zeros, and we denote the path with 1s. So this is a valid path because it consists of 1s. These are walls, the zeros are the walls. So, if it's not 1, it means that there's a wall, and we are not able to go there. It is not a valid path. But anyways, it is a valid path. So we have to check it. So if it's a valid path, we add it to the solution. It is a part of the solution, and have to go forward in the x position and check whether we are able to go there. If we are able to go there, we return true. If we are not able to go to the right position, then we try to go down. So if moving in x direction is not feasible, go down in y direction. And if it is not feasible to go down or go to the right, there is no feasible solution, so we have to backtrack. And we set the solution table back to 0. 0 means that it is not a cell in the solution. If it's 1, it means that it is a solution cell in the solution table. Okay, so anyways, we just return true, and we are going to show the results. Of course, I'm going to iterate through the solution table. If it's a 1, it means that it is a path. I'm going to denote it with S. Stands for solution, and otherwise I'm just going to put dash there. So we have to check on every iteration, first of all, whether we have finished the exit or whether it is a valid move. If it's a valid move, we add it to the solution table and try to go to the right. If it's not possible to go right, then we go down. If it's not possible, we backtrack and try to find a solution in this manner. So let's see. As you can see, this is the starting point, and this is the exit we are looking for. We can go there, 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 and there, but you can see there's a wall here, so we are not able to reach the exit. Let's see whether we are able to find it. No. Backtracking algorithm tells us that no feasible solution found. What about if I open a wall here? We are going there. I think that was the example we are considering in the theoretical section. We go here, 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 and here. We come to the solution that it is a dead end. So we backtrack and go down, down, down. Then we can go to the right, and that's the point we are looking for. So let's see. Yeah, there's a feasible solution, and yes, we have to go here, down, 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 then to the right, and that's the position we are looking for. So this is how we solve the maze problem with backtracking. Thanks for watching.